My name is Greg Statmiller, and I'm going to help you with problem number 35.2. The problem states that a converging lens with a focal length of 60 centimeters and a diverging lens with a focal length of negative 36 centimeters are 276 centimeters apart. A 2.2 centimeter tall object is 80 centimeters in front of the converging lens. Part A wants us to calculate the distance between the image and the diverging lens, while Part B needs us to calculate the image or the height of that image. Now the big thing to remember here is that we have two lenses, so we will have two images. So the image that we will be measuring or calculating, the image we are looking more into particularly is the image created by the diverging lens. Same with the height. Our known factors are that we have a 2.2 centimeter tall image. The object distance from that image to the diverging lens is 80 centimeters. And the focal length of that lens is 60 centimeters. And for the diverging lens, we only know that the focal length is negative 36 centimeters. Here I made us an interesting drawing to see the overall image of what we're working with. We have our image over here reflecting light into the lens to then project an image pretty far away. Now this image becomes the object for the diverging lens, which will send light into the diverging lens and create a virtual image. Being that this is the image we are looking more in depth to, we need to figure out the distance between the image created by the converging lens, or the real image, and the diverging lens. So we think we can then calculate the image distance of the diverging, or of the virtual image, for part A. Then for part B, we'll use similar triangles to calculate the height. But we'll just start with step 1, which is part A. In which case, we are going to use the thin lens equation, which is 1 over the focal length equals 1 over the object length plus 1 over the image length. I'm going to play with it. I manipulated this formula so that we'll get the output, our output will be 1 over the image distance. So for the converging lens, we have 1 over 60 centimeters, which is the focal length of the converging lens, subtracted by 1 over the object distance, which is 80 centimeters. Now if you plug it into the calculator, you'll get 0.00416, and then you divide this wonderful number by 1. Or you don't divide it by 1, you put it under 1. So you get the inverse to get S. But an easier and faster way to do this without a calculator is just the fact that you need to get a common factor between 60 and 80. So you can either multiply 60 by 8, or you need to either multiply 60 by 8 and 80 by 6, or you could be smart and do what I did. Multiply 60 by 4 and 80 by 3, because then you get the common factor of 40, or 240, or 240 centimeters. And having these two numbers in common, of course, when you multiply the bottom, you have to do the same thing to the numerator, which leaves us with 4 over 240 minus 3 over 240. Simplifying that gives us 1 over 240 centimeters equals 1 over the image distance for the converging lens, which gives us essentially 240 centimeters for the first distance, or the first image distance. So awesome. 240 is the number. And, with that, when you put this over 1 in the calculator, you should also get 240. So let's see. Back to our knowns. 240. Bam. Centimeters. Alright. So now that we have this number, we know it's 240, we need to subtract 240 from 276. That will easily get us 36, as shown by my math right here. 36 centimeters. Now that we have the object distance from the first image to the diverging lens, we can do the thin lens equation again. Wonderfully. So to save time and effort, I'm just going to use this formula again. Put it right over here. The focal length of the diverging lens was negative 36 centimeters. Subtract that by the distance, which we just got, which is 36 centimeters, equals 1 over our image length. Simplifying this, you get, when you subtract a positive from a negative, or a negative, positive from a negative, you add to the positive, so we're left with negative 2 over 36 centimeters equals 1 over the the image distance of the diverging lens. Simplifying it, we get negative 1 over 18, and then simplifying it even further, we get negative 18 centimeters from the diverging lens, is where our image will be found. Or essentially, overall, easier put, oh my lord, excuse me, 18 centimeters. Which is our answer for A. So let's see, 36 was here, 18 was here. Alright. So a quick recap, because I kind of flew through that one. To solve part A, you need to find the first image using the thin lens equation to get this distance, to find out the object's distance. Because, like the glasses problem from the slides, the image now acts as the object for the diverging lens. Then once you get that, you do the thin lens equation again, but this time using the focal length of the diverging lens, which was negative 36, and you'll get the object's distance, or the image's distance. Alright, A is done. B is calculating the image's height. I'm trying to be smooth here, saving time. For a stronger understanding of how to do B, check out example 34.7 for 4th edition. 3rd edition might be different, but essentially what they do is they use the image's height, or the object's height, to calculate the distance using the idea of similar triangles. Looking at a newly drawn graph of this beautiful model, this beautiful question, these two angles are equal because they are perpendicular, or they are adjacent to each other. So they should be the same. So, that's being true, then we can have the image's height over the object's height over the object's distance equals the image's height over the image's distance, being that they're equal triangles. So, let's go back to our knowns. We know that our height is 2.2 centimeters for our object, and the distance from the lens is 80 centimeters. Our image's height is unknown, that's what we're looking for, and our image's distance is 240 centimeters. Because, of course, if we're going to calculate this height, we're going to need to know this image's height. And to get this image's height, we need to know this object's height. So it's back to square one. But this will be quick, I promise. Well, anyways, let's set up our ratio. We got 2.2 centimeters over 80 centimeters equals the height of the image, which is what we're looking for, over 240 centimeters. Now, a quick statement for not using a calculator. You can easily just cross multiply, go 2.2 times 240, get like 258, I belive, and divide it by 80 to get the number we're looking for, but that's a pain in the butt. An easier way to think about it is if the denominator, if you multiply this, our initial denominator, 80, by 3, you get our final product's denominator, 240. So, to make sure this stays equal, and to keep the ratio correct, you have to multiply 2.2 to get the image's height. So, if we multiply 2.2 by 3, of course we only get 6.6 centimeters. So, this image right here, 6.6 centimeters. CM, bam, beautiful, gorgeous. All right. So now that we know that this is 6.6 centimeters tall, we can go for this image. This image's height, because we have all that we need for the ratio. So here's our another beautiful ratio. This time it's the exact same issue, or it's the exact same routine as the last. If 36 divided by 2 is 18, then we have to divide 6.6 by 2 to keep the ratio balanced. So our height, or the height for the image has to be 3.3 centimeters, which gives us B. Then again, you could also cross multiply. I didn't cross multiply this one. I just kind of decided to be simple about it. But yeah. And that's 35.2. Pretty fun problem overall. A lot of parts. A lot of painful, wonderful parts. Anyways, this has been 35.2. Done. Done and done. Both of them are correct for what I got, of course. You may have different numbers, I'm not sure. But if you do, same process, different numbers. Alright guys, good luck. Hope this helps you out.